So now we did a little playing around with the numbers in an example of calculating the uncertainty after I take two measurements and use them to do some math, particularly finding the area of a rectangle. And we realize that there are some generalizing principles. There's a rule of uncertainty analysis. And that rule happens to be, lots and lots of words, I apologize, here it goes. Whenever you multiply or divide numbers that have uncertainties, the relative uncertainty of the result is the sum of the relative uncertainty. And we did a whole bunch of conversation and calculation in order to get to that point. So what I'm going to do now is I'm going to dream up an example for you, and I'm going to solve an example all the way through. The skill that I'm about to demonstrate to you is the skill that you will be expected to do. You're going to be tested on what I'm showing you. I'm not just showing you for a good time, I'm showing you for two reasons. First reason, it's good science that science students almost never see, and you're going to be tested on it, not once, but twice. So some careful thinking, some energetic engagement in it, please. This is where can make your honors physics life quite a bit easier. That is never going to be easy. So I want to do a calculation, some kind of calculation. Which should I do? I'm going to calculate that the acceleration is equal to the velocity squared divided by twice x. Now, later on in your physics course, matter of fact, very soon, that equation is going to be an equation you use all the time. It's going to be simple and obvious to you. Right now, it's just a bunch of gobbledygook. But that is a physics equation. It's a relationship. To calculate acceleration. But I can't do the calculation unless I first make a measurement of velocity and make a measurement of position. That's what x is in this equation. So to make up like say this was going to be your quiz, I have to make up some measurements. So let's say I go out, I want to calculate this thing. So I go out and I measure the velocity. And again, I'm just making these numbers up. I measure the velocity of the thing and I find it to be 5.21 plus or minus 0.01 meters per second. I just made that number up. And if you're not comfortable with the units of velocity being meters per second, don't worry about that. This discussion is not about the units of a quantity. It's about how I calculate the uncertainty. So there's a measurement that I made of velocity. And I'll point out immediately, look what happens. I just made a number up, but I couldn't write anything that I wanted. Hundredths. The precision of the uncertainty matches the precision of the measurement. Look, 3 significant digits, 1 significant digit. It's not an issue of Sig Figs. The precision of the uncertainty must match. So when I make up this next number that is x, and I say that it's 6.2 plus or minus 0.1 meters, look, I did it again. Tenths. The precision of the uncertainty matches the precision of the measurement itself. That's critical. You may want to fiddle around with Sig Figs on the uncertainty. Don't ever do that. Significant figures applies to the measurement, not the uncertainty. Okay, so now I got to get busy solving the problem. The question here is, these are the measurements that have been made, velocity and position. Calculate the acceleration and its associated uncertainty. So as I said over here, I'm going to make a list of the steps that I take to accomplish this. So the first thing on my list, step number 1, is the favoritist step of all the steps. Just do it. The first step in doing an uncertainty problem of this nature is to pretend like uncertainty doesn't even matter, you've never heard of it, and simply calculate what the acceleration is. So calculators, please, because I can't do it in my head. Calculate what the acceleration is based on the velocity being 5.21 and the position being 6.2. So 5.21 squared divided by 2 times 6.2. I think Phil's going to get it first. No, I'm wrong about that. 2.189. 2.189. You know, I'm hesitating to say your name. I feel as though I forgot it. For some reason, I want to say Justin. Oh, there you have it. Just rattling around inside my skull. 2.189. Gave me lots of digits because Justin knows now is not the time to be rounding. But Shannon, how many digits should I keep? Keep enough so when you get to the very end of the problem, you have to round. If you round too early, you might accidentally round away significant digits, and we don't want to do that. So to be safe, we keep a slew of digits on there. So there we go, just do it. If we were not in this physics class, that would probably be considered an acceptable answer. Thankfully, We're going to go on and do it scientifically. The very next step that I want to put on my list, the next thing I have to do, is to appreciate that it's a relationship among the relative uncertainties. Pardon me for not writing it out. It's a relationship among the relative uncertainties. So I have my measurements here with their absolute uncertainties. I need to calculate them with their relative uncertainties. So for the velocity here, I need to calculate the relative uncertainty, and that's the percentage. So if you would for me, calculating the percentages is 0.01 divided by 5.21 times 100. And what percent is that? 0.192%? That is a small percentage. But look at how small the uncertainty is. So that makes sense. I get a small percentage for the uncertainty. That's a good measurement. That's a very good measurement because that's a small uncertainty. Everybody agree with this? Okay. I need to find the relative uncertainty of my measurement of position here. That's 0.1 divided by 6.2. That's not going to work out so well, or as well. 1.612. Excellent. Now I've calculated the relative uncertainties of these numbers. I'm ready to move on to the next step. 613. And it turns out that's far enough out in the decimals that that little mistake wouldn't have done anything. Now it's time to apply the rule. And I'm not going to write that rule out here on the list. I'm simply going to say, rule. The next thing to do is to apply the rule. I'll recite the rule again for the record. Whenever I multiply or divide numbers that have uncertainties, the uncertainty of the result is the sum of the relative uncertainties. But look, I've thrown a wrinkle in. Oh, I will repeat again, shall I? Whenever I multiply or divide numbers that have uncertainty, the relative uncertainty of the result is the sum of the relative uncertainty. Yeah? So, I've thrown a wrinkle into this one. The v is squared. The v is squared. I don't have a rule for that. Yes, I do. To square v, I have to multiply v by itself. Isn't v squared v times v? So, the first part of the calculation is do v times v. So what do? I add the relative uncertainties. So that is 0.192% plus 0.192%. Do you see what I did there? I'm multiplying v times v. So I add the relative uncertainty of v to the relative uncertainty of v. I'm not done yet. I'm just pointing out that because it's v times v, I'm adding the relative uncertainty of v to the relative uncertainty of v. You know, Scheidly, that's weird because it's just 2 times v. I'm sorry, 2 times the relative uncertainty. Squaring a number doubles its relative uncertainty. Squaring a number doubles its relative uncertainty. What would happen if I cubed it? Triple. What would happen if I raised it to the 4th power? Quadrupled. What would happen if I raised it to the 5th power? Quintupled. I just actually went that far to see if anybody would say quintupled. Well done. So it seems like there's like a sub-rule that's not really a rule, but it's kind of there, that whenever you raise a number that has uncertainty to the power, you multiply the relative uncertainty by the power. Ready? Ready to take it to the next level? What would I do if I had a measurement that was square rooted? Half the relative uncertainty because a square root is raised to the 1/2 power. Yeah? Aren't we clever? But I'm not dealing with that here. Once I've multiplied v by v and added those uncertainties, then I divide by x. Multiplication or division, it's the same. I add the relative uncertainty. So the uncertainty of the result is the sum of the relative uncertainties for every operation that I have to do in order to get my answer. So what does this all add up to? 1.805. 1.805. Okay, now 1.997%. That means that my answer is now that the acceleration is equal to 2.198 plus or minus 1.997%. I am not done. I am not done for several reasons. I got to do a little cleanup now. Now that I've applied the rule, I've got to clean my result up a little bit. And so step 4 here is going to be to calculate the absolute uncertainty. I don't want the relative uncertainty for my answer. I want its absolute uncertainty. So the question becomes, what is 1.997% of 2.189? And the way that you calculate that, of course, is you take 1.997, divide it by 100, and then multiply it by 2.189. The question is, what is 1.997% of 2.189? Did I do that? Did I write that right? Somebody confirm? Yes, but I'm not done. Justin originally gave me the number as 2.189, the measurement. I can't have that many significant figures in the answer. So step 5 of this process is to correct the Sig Figs of the answer. Step number 5 of the process is correct the Sig Figs. The Sig Figs don't affect the uncertainty. Leave the uncertainty alone. The Sig Figs apply to the measurement. The Sig Figs apply to the measurement because I calculated this number using the velocity, which has 3 significant figures, and the position, which has 2 significant figures. A chain is only as strong as its weakest link, and so my answer can only have 2 significant figures. And so I'll write the acceleration as, rounding this, 2.2 plus or minus 0.0437. I did. We have to reiterate it because apparently it's the most difficult thing to remember about this. I do not adjust the significant figures of the uncertainty ever. Yeah, but Charlie, what about ever? Yeah, but in this one, it's ever. Okay? What do you think? I asked the question, what is 1.997% of this number? And that is the answer. So I computed by taking 1.997, dividing by 100, and multiplying it by 2.189, and that's what you get. Apparently, that's what they tell me. Last step has nothing to do with Sig Figs at all. Are you listening to me? I certainly hope so. No, it's not the labeling. You have to match the precision. Look, everyone, hundredths, tenths. Every correctly written scientific number with uncertainty that I've written, the precision matches. You can see that this is out of wonk, isn't it? This is tenths, and this must be tenths. So I round it till it's tenths. It rounds to 0. So I'll write this as 2.2 plus or minus 0.0. 0 uncertainty. Exact. No, I can't do that, can I? I can't do that. There's no such thing as 0 uncertainty. So what am I going to do? Yeah, I'll round up. So the acceleration, my answer is 2.2 plus or minus 0.1 meters per second squared. Don't worry about not knowing those units. You will soon enough. Tenths. Hundredths. Matching precision for the uncertainty. Now, are you ready to have a lash at it? As you see, I have provided you with the ruler, although for some of you the ruler has disappeared. What I would like you to do, please, and remember, the first time that we did this, I said, I'm not going to answer any questions. Not going to give you a limited explanation. That's because, of course, I wanted it to go as badly as it possibly could so that we could correct it. Now I'm going to give you a little bit of instruction. First of all, detail-wise, we're measuring the top of the table. No problem of definition. Measure the length of the table and the width of the table. Now listen carefully. This meter stick has millimeters on it. I don't want to use the millimeter. This meter stick has half centimeters on it. I don't want to use the half centimeters. I'm asking you, here is your task. Please determine the surface area of the table by measuring the length and the width of the table to the nearest 1 centimeter, right? I'm actually making it easier on you than it would otherwise be. Measure it to the nearest 1 centimeter. When you're done, send a representative from your table to the board to write down your answer. Fantastic. And by fantastic, I mean we completed the activity. Once you get past that part of it, every single one is wrong. Every single one. Before I say anything, Owen would like to change his answer. You seriously got up from your chair so that you could walk over there and make it worse? No. There's no close. Did you have an argument about that being the answer and someone lost? I'm going to ask somebody else to explain why I wrote that as 200. Now, the uncertainty is the problem, right? So don't talk to me about Sig Figs. Okay, can somebody tell me why I write 200 to be correct? Yeah. Well, in principle, what I think you're doing there is restating what the rule is, that I have to match precision. Look. Hundreds, tenths. Hundreds. You guys just don't like being on the left side of the decimal point, do you? But Charlie, what about that? Those 2 zeros there, they're not significant. How do you know? You rounded it so that they would only, the 9 and the 3 were the only significant digits. You know that the zeros aren't because you rounded it to make it that way. You're the one who did that. Which means the 3 is the first significant digit in the number, which means the precision of that number, 9,300, is the hundreds place. Yeah? Fantastic. Well, if nothing else, hey, upside, most of us got the same answer, as opposed to a board full of all different answers. I mean, at least we're heading in the right direction. A person of your age should not say things like that. That's not what you said. You said we don't know how to round. What did you say? What's that? Someone on my side? That's what I heard. Doesn't matter who's friends with whom, it got recorded. So we'll go back to the recording and see what happened. So clear that before you get tested or quizzed on this, you're going to want to practice up some more until you're reliably getting correct answers, right?